between the electron. Then I'm sending the one of the electrons there. There must be some things happen in the bottom layer, right? And if you use this external language, then you can easily understand what is happening. Because now the electrons on top layer couple with the empty spot of these electrons there. In other words, hole is coupled, right? I'm just kind of pushing the electron in the top layer, then you have to push the hole in the bottom layer in the same directions, right? So this type of the thing start to tell us, say, for example, there's a perfect drag effect happens. If I send the electrons in this side, current is flowing there, the bottom layer should send the current in the opposite layer. These things happen. If I just make the current loop or current return, and then perfect drag should happen. And there are a few experimental consequences has been measured in this experiment. One of the evidence is basically when you measure so-called the drag hole measurement, send the current in the top layer and measure the voltage, hole voltage in bottom layer, then you get this the perfect, the quantized, the whole drag hole effect appears as if as a whole layer that you measure the drag hole effect appears, and that has been measured into the quantum or bilayer system, and that is considerations, one of the evidence that indeed we can create those kind of correlated state between the electron hole and top and bottom layer, and one can view as extern condensation, or more precisely magnetic extern condensations, right? So this has been the physics already known for past 20 years, maybe close now 30 years. Yes, go ahead. Yeah, please. Yeah. No. I think this is good. Yeah.
You have these two 2D gas.
Yeah.
They are coupled to the intermediate layer.
Yeah.
So how do you really create an electric field on the top one which is not affecting the bottom?
Electric field.
So to pass the current.
Yes, I think so. I can write here, right? Yeah. Some of this, and then, so this is top layer and bottom layer. And if I just simply bias this, right?
So this is not coupled to the bottom?
Yes. So experiment is basically done that there's some insulators in between, right? And then I just send the current. So I'm sending the current in these directions, right? Say, for example, then I can measure the current in that directions, right? In this way, right?
So the coupling is via this insulating layer?
Yes. So coupling is basically, there is no real direct electrical coupling. If you measure the voltage resistance across this one, this is gigaohm, right? But then weird things happens in this experiment. If I just send the current like this, and then simply short this bottom layer and just try to monitor the current, and then what you see here is that the bottom layers carry the current, but the current should be opposite directions, right? And the reason is clear because here that if I have the electrons there, that the holes there, hole is coupled with the electrons by just Coulomb interactions I just kind of talking about, right?
This is DC current, right?
DC currents, but also you can just do the AC measurements as well, right? Yeah.
DC is more surprising.
Yes, yeah. And the DC, I think, even if we use AC current, that's a low frequency AC current. So it's actually in this language is quasi-DC, right? So this was actually kind of done already, well established in gallium arsenide. Jim Eisenstein and Caltech got his fame out of this very difficult experiments. And this experiment is difficult because if you think about these quantum heterostructures made, right? You should be able to make the individual contact in both of the layer, and this layer is only few 10 nanometers apart. So how to make this contact, and the Eisenstein group went through a lot of this technical innovation to do this experiment.
So there might be a critical thickness through which...
That's right, yeah. So we will get there in a moment, right? So now I'm just bringing up this old experiment because I want to show that, okay, so of course we can do experiment with the graphene, right? All the 2D materials. Now, okay, so I mentioned that we can stack them, we can make the kind of individual contact. All the technology is there, right? But what you can do more? Well, so we have a little bit of the advantage over the gallium arsenide heterostructures. First of all, that we can put the gates everywhere. Because of technical reason, gallium arsenide, putting the gate everywhere is a little bit difficult, right? But we can put the gate everywhere, and we can use the graphene, which means that it can be electrons, it can be holes, depends on the gate voltages, and quality is high enough now And furthermore, that you can put this two graphene layer very close by, right? Because hexaboron nitride, which actually I can separate, can be as thin as, say, 1 nanometer or even thinner, right? Compared with this, the gallium arsenide heterostructures, where that because of all this, the growth issues, the two layers are about 10 nanometers away. In graphene, that we can put into the extremely close by, without even just tunneling, right? Which means that I can create this, the binding energy of the electron holes that I just mentioned becomes even larger, right? So it becomes really robust, the experiments one can realize. Indeed, not surprisingly, once you do that, we start to see that all this, for example, in this experiment, I'm showing this drag hole measurement, which actually supposed to be quantized when these two-layer couples and make the axion condensation, start to appear in the experiments, right? Here that the bottom filling fraction and top filling fractions can be controlled by the gate voltages. And this, the range is where that you get the finite drag hole, which means there's a layers couple. If you just zoom in that, actually that shows a nice quantization behavior, V entrant quantum Or. Basically, using the language of what you learned from the 2D semiconductor heterostructures, that we know that this is basically where that my magnetic exchange condensated along this line, where the total filling fraction is 1. Another interesting part is it's not only that between these two lowest Landau level, which has been demonstrated in gallium arsenide, any half-fill Landau level, in fact, as long as their symmetry actually matches, can create those kind of the axion condensation, magnetic axion condensation. So there are many different kinds of the magnetic axion condensation can be realized. Yes? Yeah.
I understand that the top and the bottom layer get coupled in those corners.
Right.
So, now condensation, of course, normally in superfluidity, let's say, or superconductivity is associated with something dissipation less. Here, what is the sort of signature of the condensation?
Yes,
What
right.
is, for example, the difference between this excitons not being condensed and being condensed?
Right. So that's actually very important questions and good questions. Right. So again, in gallium arsenide, so there are several evidence has been demonstrated. One is basically this perfect drag, right? And when you send the current here, then you get the current here, same amount, and that's basically tells us perfect drag. And the other one is instead of doing this, you can actually doing the following things. So I'm sending the current in this direction, I, right? But then I just connect these two and get this one back, right? And ask that what is happening. Then I get in here. I comes out, of course, right? But what happened here is basically because of in here, if it is condensating, it's kind of the extern is flowing like this, but there should be no dissipations at all, right? So in this experiment, basically it was demonstrated then you can get the dissipationless current. It's what we call the perfect drag geometry, right? And this, perfect counterflow geometry, sorry. And that is another evidence of this, so there's a superfluidic flow of the extern is happening. That is not coherence yet. Coherence can be demonstrated by just looking at this tunneling between these two layers, and then there's kind of some sort of the coherence peak appears in the tunneling spectroscopies. So there are some of the evidence kind of accumulated in the gallium arsenide showing that indeed this is really coherent many-body states. Right? So we basically borrow very similar things in graphene, and we don't yet demonstrate everything, but at least kind of some things, very analogous things happen. So that's good.
Philip, just
Yes.
a quick
Yeah.
thing. So you said that one of the advantages of the graphene was you could bring them really
Yeah.
close.
Yeah.
Earlier you mentioned that the cross-layer resistance was in giga-ohms.
Yeah.
Even at a nanometer separation.
Okay, so that's a good point. Of course, if you want a greedy and I want a really strong binding, you want to kind of put them together, right? But of course, then what happens is there is strong tunnelings happening. So you have to find the sweet spot. It turns out about 1 nanometer and above the boron nitride, say 3 layers and above, you strongly suppress the tunneling between them. So it's okay. But below that 3 layers limits, then you start to suffer from the tunneling between them, which actually spoils all this solid dimension, right? So there is some sweet spot you have to choose. Right, but nice thing about the graphene is now one can do a few different things which has not been done in gallium arsenide. For example, that you can, instead of creating electrons and holes, that I use in the magnetic exciton, the language of the hole, in a sense, is missing electrons into the electron Landau level, right? But instead of doing that, you can actually put the real holes there, right? Simply, I just put the gate voltage on the top positive, bottom negative, populated electrons on one side and hole the other side, right? So you can create a really the excitons insulators where the real electrons holes together, and ask that what is going to happen on those kind of the case where instead of you have exciton, well, in a sense that magnetic exciton is a weird case because you get condensation, but you have this quantum or edge states. In fancy word, this is basically exciton topological insulator in a sense because the inside is condensated becomes the insulators, but the actual current can flow at the edge state through these quantum edges. But if you make the electron Landau level, electron and holes in the opposite side, in the equal amount of this equal but opposite the density, equal density but opposite sign, then you can create a really exciton insulator in this system which is not conducting, right? So in principle, we can just do that. Say again, this is a top and bottom density, and this line along here is basically in total, you get the zero density, right? You can see the whole voltage in the whole direct voltage here is all blue, and this is red, means it's opposite sign. Along this line, we expect it's a compensatory field. Indeed, if you just look at this line and carefully, the following situation can be made. Okay, so this is a little bit busy plot, but I can show you here. So this is basically along this gate voltage, I just cut it through that measuring different the conductivities and longitudinal and the transverse conductivity. But you can see that as I just sweep through this one, top and bottom densities goes opposite, and this is a point where this kind of two layers are compensating each other, right? At this point, what you see here is basically everything goes to zero. Both the longitudinal conductivity and the transverse conductivity goes zero. Or even if you measure this two-terminal conductance, it actually goes to zero, which means that if I just have these two layers together and I measure how this current flow, this two layer shows that, well, it's basically bad metal, or actually it's an insulator, right? So that's actually a little bit weird case, right? Because I told you that even in this line, each of the layer is a partially filled Landau level. So it is the bad conductor, but still conductor, right? And then you just put these two conductors together, right? But then you have the little bit better conductions. But instead of you get a little bit better conduction, you just quench the conductions. It becomes an insulator, right? And why does that happen? Actually, that is demonstration. You have the electrons, holes, they correlate each other, and because I'm sending the current through this system, right? And if the electrons and holes are strongly bound, that basically this exciton need to move, and the current should be canceled. Top layer is current in that direction, bottom layer current is opposite direction, as the total current goes to zero, right? So that's basically what we get the exciton insulator. However, as I said in that drawing, if I just make the connections if I just send the current only one direction and measure the current in the bottom layer, the so-called perfect drag, or the other geometry, if I just return, counterflow or perfect counterflow should happen. And indeed, in these experiments, at exactly this insulating point, you start to see that perfect drag current drag happens. So indeed, we can create this condensation into the system when electrons and holes are populating in opposite directions. Okay, so that's actually kind of something we can realize. But the really interesting part is now, if you just really believe that this is an exciton insulator, right? You can ask that, okay, so how they actually behave in different temperature. And you know that you can also change the magnetic field and ask that how these exciton insulators in this compensated field state actually got changes. So if I just kind of map it out, and that particular exciton insulator we just have at a different temperature and different magnetic field, and this is a result. I'm showing you here that this is basically conductance that we are getting into the system. So this red part is basically where you get the zero resistivity, zero conductivity. So this is basically where we have the external insulator. And blue means actually now there's conduction is happening, so there's no external condensation. So you can kind of read it off. What is a phase diagram should look like? Anything in red is basically I have the external insulator. Anything blue is basically it becomes conductor, right? So you can see that external condensation is happening somewhere there, right? And there's an interesting phase diagram, so you can read it off. It's starting from, say, low temperature. If I call this is transition temperature, basically it shows some sort of the interesting dome-like the shapes, right? Well, you can actually study a little bit carefully. So you can also set that how this temperature behavior look like, and you can see that there is activating behavior, and this activation behavior give us the activation gap of 6 Kelvin, which is actually substantially larger than this energy scale. So if you just kind of believe this is some sort of binding energies or something, that may actually relate with external formations, but then this is somewhere that external condensation type of things. And when you go to the high magnetic field, basically that activation behavior is exactly gone away, and it's more like the sharp transition is happening. So it's more look like, if you just kind of simply look at some of the conduction is really quenching off, I think this look like some of the superconducting like the transition. So there's some of the regime change, you can read it off from this type of the diagram. This is yet really qualitative descriptions, but already start to sense that interesting dome-like the shape of the transition is happening. In fact, this type of the things is exactly expected when you just look at these electrons or holes and form the extons. Theory already expect then when you have this exton, and especially stable exton is long-lived, there are different phase diagrams you can just kind of draw in this simple drawing. So in this simple drawing, eventually if you go to the high temperature, exton will be just kind of just freely move around, exton gas is there. But then if you go cool down the exton gas in the low enough temperature, eventually that exton will condensate into the Bose-Einstein condensation. So you get this the constant condensate extons with certain transitions. However, there's one knob that we can just turn around. We can just tune the exton density.